In this video, I'm just going to be going over some problems that deal with Lenz's law. The idea is that we want to figure out what is the direction of the induced current through a circuit. We're going to start off with the easiest one here, where we picture this being a very long wire with a current going through it. Now, if the current's just going through it at a constant speed, so all the little charges are moving along with a constant speed, we're still going to get this induced magnetic field. That's going to be, if we use the right-hand rule, like this on this side, and then this on this side, right? So it's going into the page and then out of the page. This into the page magnetic field is going to be down here as well, right? So we can draw it, and it's going to be something like this, right? Now here, we are told that this current rapidly decreases. So we have this change in the flux. So originally we just had these lines, these magnetic field lines going into the page. All of a sudden, this decreases, which means we get less of these into the page field lines. The induced current is such to compensate this. So here we're losing these little x's. So that means that our current is going to be such to create new x's for us, right? And to be able to do that, by our right-hand rule, the current has to flow in this direction. So it has to flow in this clockwise direction, again, just using the right-hand rule. So we say that the current inside the loop is such that this is induced, current is clockwise. Let's move on to this problem here, where this is just a solenoid, right? So the solenoid is wrapped around some object, it doesn't really matter. And then way down here, we also have the circuit that's also wrapped around like this with some resistor here. So originally, the switch is open, and then at some point, it is going to be thrown closed. So whenever the switch is closed, the current throughout this solenoid, it starts moving, and it goes clockwise. It goes like this. We can just draw that out with an arrow. So this is our current here, right? Now, this is going to give us a magnetic field inside here, right? And we know from the solenoid the magnetic field is going to be pretty uniform, and it's going to look like this here. Okay, so because we have this, we essentially get this increase in magnetic field through here, going specifically in this right direction. So through our circuit here, we have a magnetic field going to the right. The current is going to be such to oppose this. So by opposing, it's going to induce a magnetic field that's going to the left, right? So its magnetic field is going to go this way. And to be able to do that, essentially what needs to happen is that we have this inside of it, right? So we have this magnetic field going like this, and to get that, we have current going in this direction. So again, if we use the right-hand rule, the current is going counterclockwise to oppose this change in magnetic field motion that we get here. All right, so lastly, we're going to move on to this problem, where it's a little bit different. And here we have this magnet that we're moving away from the solenoid system. So if we think about the magnet, it looks something like this, where the north side has these field lines going in this direction and the south in this direction. So essentially what's happening is originally we had these field lines going like this, and as we move this magnet to the left, we get this decrease in field lines like this. So because we're losing these field lines, what's going to happen is our circuit is going to compensate and give us back the field lines essentially. So this here, this system is going to be such to induce this new magnetic field that is also in this direction. You can also think of it as something like this, right? Where here we have the north side, we have these lines that are going here, and we're moving it away, so then we have less of these lines. So the magnetic field induced is in this direction. So again, by the right-hand rule, that means the current has to be going in this direction. And it's the same thing here, right? So our current is going to be flowing like this. So if we draw it out, we have the current going like so, okay? So that's about it. Really, the only thing you need to remember when you have all of this is, well, to know what's happening, right? Like, where are your original magnetic field lines? Like here, we had something originally. Here, we had nothing originally. And here, we also had something originally, but it was all a little bit different. Then we have to know, how are these lines changing? And we have to know that essentially the system wants balance. It wants order. Like, it doesn't want things to change. So it's going to do essentially the opposite of that change to balance things back out. And that's, in essence, what Lenz's law is. Okay?